So, good evening. I'm Julian Urain, a PhD student in TU Darmstadt, and I'm happy to present our work on learning stable vector fields on Lie groups. The goal of our work is to find a general learnable model architecture that allows us to represent arbitrary complex robot skills as the ones that we can observe in the videos. We are looking for a single model that can represent the motion for any of these tasks and be able to adapt to an environment. So, what are the essential elements that define these robot skills? Those that are shared along all these different tasks. So, the first and most important element is that we can represent these skills as dynamical systems. A dynamical system, here represented with the F, will provide the desired robot acceleration given its current position and velocity. Then, to control the robot, we can apply some low-level controller to map these accelerations to a torque signal in the robot. Additionally, there exists a set of properties that are essential for most of the robot skills. In our work, we consider three. First, stability. If we observe most of the robot skills, they are reaching tasks towards a certain target pose or limit cycle. Second is geometry. Most of the robot tasks can be defined in rather the robot's end effector space or in the object space. To properly deal with the orientation of the task space, we need to model the dynamics on the Lie group. Finally, expressivity. The learned model should be able to represent highly nonlinear movements and adapt to arbitrary scenes. So, let's start simple. How can we build a model that is globally stable? A common approach is to evaluate the Lyapunov stability of a chosen dynamical system. Let us assume, for example, a quadratic Lyapunov function with the dynamics models represented as the gradient of this Lyapunov function. The first two conditions are satisfied due to the selection of the Lyapunov function, and for the third case, we can observe that by changing the dynamical system in the third equation, we satisfied it also. If we evolve any particle from any initial configuration with the given dynamics, we will arrive to a stable behavior. Yet, these dynamics are linear and we cannot represent complex behaviors. How can we represent nonlinear stable dynamics? So, a possibility is by exploiting the invertible neural networks. Let us consider a diffeomorphic function phi that maps the latent space set with the original space X. Then, given a potential in the latent space and the mapping phi, we can represent the potential function for the original space as U. If we define our dynamics as the gradient of this potential, we can represent these dynamics as the Jacobian pseudo-inverse of the mapping times the gradient of the latent potential. So it is important to remark that this mapping phi is a diffeomorphism. A diffeomorphism can be thought as a space deformation, as we have shown here. So this will be the original space and this will be the latent space. If we apply this space deformation over the potential, we're gonna get a deformed potential field. Nevertheless, this potential field, if we follow the gradient, we will still be stable, as we can observe here. These dynamics are guaranteed to be globally stable, but additionally are highly nonlinear. So, one of the limitations of this approach is that it is limited to Euclidean spaces. Nevertheless, to represent the robot's both position and orientation, we need to deal with non-Euclidean spaces such as the Lie group C3. How can we do that? So, in our work, we exploit the tangent space of the Lie group C3. Let me provide an intuition with SO3. The sphere in the right is the tangent space on the identity matrix of the rotation matrix. For any rotation matrix, there exists a point in the p radius that maps to this rotation. While the rotation matrix is not Euclidean, the tangent space is. Then in our work, we propose learning the dynamics directly in the tangent space, such as we can guarantee the stability easily. Without going into much details, in our work, we exploit this tangent space. Given any point in SE3, we first map it with the log map to the tangent space on the identity. Then we learn the dynamical system in this tangent space, and the obtained vector is going to be represented in the tangent space of the identity. If we want to map it to the vector on the tangent space of the input, we can do it through the adjoint operator and then obtain the Cartesian, like the positional and the orientation velocities with respect to the tangent space of the input. In the following, we show the results of the learned vector field for a Turing task. We provided a set of demonstrations and learned to mimic the teached behavior. As we can observe, the robot behavior is stable both in position and orientation, and in the end effect, defined in the end effector. Additionally, even if we perturb the robot, it easily adapts and keeps going to the target. In conclusion, we have proposed a novel vector field model that can learn globally stable and highly expressive vector fields in Lie groups, and we have proved its performance under both human perturbances and even scene modifications. Thank you.